Splitting or addition of determinants. First, suppose if this is the determinant given to you, then you can write this determinant as A1, B1, C1, and remaining two rows will remain as it is, plus the determinant of X, Y, Z, and remaining two rows will remain as it is. What I'm doing here, I'm just splitting the elements in the first row and writing the individual determinants and keeping the same second and third row as it is. So how to prove this? So let us calculate this individual determinants on RHS side. So from here, if you calculate the determinant, you will write it as A1. Consider the cofactors. So it becomes C11 plus B1, C12 plus C1, C13. So these are the cofactors of particular elements. This is how the determinant comes out. So basically, and plus write as it is, calculate its determinant now. So when you do that, X into C11 again. Why again? Because these elements are same, na? So it becomes just C11 plus Y into C12 plus Z into C13. So just take common. When you take C11 common, you'll get A1 plus X, C11 plus B1 plus Y, C12 plus C1 plus Z, C13. So this is actually what this determinant value is. Am I right? So here, one thing to remember here is you can split only a particular column at a time or a particular row at a time, not two rows at a time, because when you do that, this cofactor is going to change and will it not satisfy the LHS side. So basically, if you have a sum of elements, addition of elements in the determinant, you can split it by taking any one row or column at a time. So let's see a few questions on this. In this question, we need to find the total number of distinct values of x, and all x belongs to real numbers for which this determinant is equal to 10. So here we need to apply the splitting of determinants concept. So to which row or which column you need to apply this? To the third column. So it becomes x, first two columns remain as it is, 4x square, 9x square, 1, 1, 1, plus again the first two columns remain as it is. The third column elements are x cube, 8x cube, 27x cube, and this value is equal to 10. From here, from the first column you can take x common, from the second column you can take x square common. So x into x square, 1, 2, 3, 1, 4, 9, 1, 1, 1. So similarly here you can take x common, x square and x cube. So the remaining is 1, 2, 3, 1, 4, 9, 1, 1, 8, 27 is equal to 10. So it becomes, now apply the column transformation and make it in such a way that these and these values becomes 0. So how to do this? You can apply column 2 changes to column 2 minus column 1 and column 3 changes to column 3 minus column 1. So when you do this, here it becomes x cube and inside column 1 remain as it is. Column 2 changes to 2 minus 1. So 1 minus 1 0, 4 minus 2 2, 9 minus 3 6, and column 3 also changes. So 1 minus 1 0, 1 minus 2 minus 1, 1 minus 3 minus 2. Similarly here plus x power 6 and column 1 remain as it is 1 2 3, column 2 changes as C2 minus C1. So 0, 2, 6, and C3 minus C1 0, 8 minus 2 6, 27 minus 3 24, and this is equal to 10. Now just take the determinant, that is x cube and into minus 4 plus 6 plus x power 6, 24 2s are 48 minus 6 6 are 36 is equal to 10. So it's nothing but 2x cube plus 12 x power 6 is equal to 10. So it's nothing but x cube plus 6 x power 6 minus 5 equal to 0. And now assume x cube as t. So when you do this, it becomes a quadratic equation. How? 6x power 6, which is nothing but x cube is t, x cube whole square is nothing but t square, which is nothing but x power 6 is t square, plus t minus 5 equal to 0. So this is nothing but 6t square plus 6t minus 5t minus 5 equal to 0. You can take 6t common from here, t plus 1 minus 5 common, t plus 1. So t plus 1 and 60 minus 5 are the two factors over here, and you will get t equal to minus 1 and t equal to 5 by 6. But we need to find the values of x. So x cube is equal to t. So there are two possibilities. Those are x cube is equal to minus 1, x cube is equal to 5 by 6. So from here, x is equal to minus 1 whole power 1 by 3. So from here we'll get only one real number of x, that is x is equal to minus 1. The remaining two roots will be some complex number, but in the question only real numbers are asked. So from here we'll get one value of x. From here x is nothing but 5 by 6 whole power 1 by 3, which is a real number. So according to the question, we need to find the total number of distinct x values, and they should belong to a real number. So therefore the total number of distinct values of x are 2. Those are minus 1 and 5 by 6 whole power 1 by 3. So 2 is the correct answer to this question. So in this question, it is told that both A and B are the square matrices of order 3, such that determinant of A value is given and determinant of B value is given, and we need to find determinant of 3AB. So just now we have seen a property that determinant of K into A is nothing but K power n into determinant of A, where K is a constant and n is the order. So similarly, here determinant of 3AB can be written as K is nothing but 3 over here, and what is the order? That is 3. So it becomes 3 cube determinant AB, and AB can be split into determinant of A and determinant of B. So it's nothing but 27. What is the determinant of A value? Minus 1. Determinant of B is 3. So it's nothing but minus 81. So option B is the correct answer to this question. Important results. The first one is the determinant of skew symmetric matrix of odd order is always a 0. How to prove this? What is a skew symmetric matrix? When a matrix is said to be skew symmetric, what is the condition? The condition is A transpose should be equal to minus A. So the determinant of this skew symmetric, that is, now we have studied a property that determinant of A transpose can be written as determinant of A. And from here, if we take minus 1 common and whole power n, determinant of A will left out. So, and it is told that of odd order. So here n is a odd number. So when it is an odd number, obviously minus will remain and determinant of A will come. So when it comes to the LHS side, it becomes 2 times of determinant A equal to 0, and from here we can say that determinant of A is 0. So determinant of skew symmetric matrix of odd order will always be a 0. Determinant of diagonal matrix is equal to the product of its diagonal elements. How? First, suppose if a matrix is there, that is A, it is a diagonal matrix. So diagonal elements will be ABC for suppose, and the remaining elements will always be a 0 in this. So when you calculate its determinant, so how we'll do this? A11, that is A, M11 is B00C, as A12, A13 are 0 and 0, something you multiply with 0, you'll get a 0. So from here we can write it as A BC minus 0, which is nothing but ABC. So that's what it is. When you take the determinant of diagonal matrix, this is equal to the product of its diagonal elements. The third important result is matrix whose determinant is 0, then that matrix is called as a singular matrix. Otherwise, it is called as a non-singular matrix. For example, if a matrix A is there and its determinant is 0, then this matrix A is called as singular matrix. If determinant of A is not equal to 0, then A is called as non-singular matrix. So these are the 3 important results you need to remember.